All right, so this is the last lecture on experimental design, and then we will generalize in every possible way. You could have any number of factors, any number of levels, any number of repetitions. Okay. So we'll talk about what is the model for the general case, how do you analyze it, and then we talk about three methods which are very informal and very easy to do. We have factors. You have 2 raised to k minus 1 effects. 2 raised to k minus 1 effects. Out of them, k are the main effects. K sub 2, KC2, 2 factor interaction, KC3, 3 factor interactions, and so on. So here's the example. Suppose you have 3 factors, A, B, C. Then you have alpha, beta, and y. And then you have gamma, A, B. So that is the interaction between A and B. Then you have interaction between A and C. Then you have interaction between B and C. That is the second order interaction, K sub 2. So that is 3C2 is the 3 second order interactions plus K sub 3. KC3 is the KC3 is 1 third order interaction. Right? Now if you just make it 4 factors, then you will have 4 main effects. And how many second order effects? Anybody? If you had 4 factors, how many second order effects? Formula is right here. Yeah, and that would be 4. Say 4 choose 2, right? Right? So that will be how much? Nobody can calculate 4 choose 2? Huh? 4 times 3 divided by 2. 1 times 2, right? 4 times 3 divided by 2 is 6. And what would those 6 would be? Can you enumerate them? First start with A. AB, AC, AD. Then, once you're done with A, then start with B. BC, BD. That is 5 so far. And then once you're done with B, then start with C. CD. That is it. 6 second order effects, right? So what if you had them, now how many third order effects you will have in that design? Four, choose 3, that is 4. And those will be, start with A, ABC, ABD, right, ACD. 3 right there. Now go to B, and you get BCD, and that's the end. And so on and so forth. So you will have many interactions. All right, everybody awake? All right. So the analysis is very similar to factor design, though. Basically, you have to write down alpha, beta, gamma, whatever you have, and then you have to write down all the dots, all the means. So if you take the mean along all the dimensions, you get bar, which is the overall mean. If you take the dimension along I, you get alpha I. If you take along the second dimension, you get beta, and so on and so forth. So whatever dimension you take the mean to, you get that thing. And you can get the sum of the squares for each of these effects and interactions, and you can get the F test exactly as before. I will do with this study. This is a real study. So we have 4 factors: page replacement, deck arrangement, problem program, and memory page. There are 4 factors, and each of them has 3 levels. So this is nothing with the 2 raised to 4 or 2 raised to 3. This is just general, right? This is like 3 raised to 4 design in some sense, right? So it has 3 levels. There are 3 replacement algorithms, 3 deck arrangements, programs, 3 memory pages size. All right, and here is the raw data. So they ran all these experiments. But the y max to y min is very large. Right? So they said, let's try the log transformation. But after the log, things are more edible, yeah. And then once we do this, then we all we do is take the mean along several dimensions to get that particular effect. And so you can get, for example, mean along the first effect. So let's try to do that. So we want the first effect is LRU small. Sorry, LRU V, which could be small, medium, or large. So the small ones, we just add up all the things which are small. Okay? So we add up all of these numbers. They are all small. Right? And we divide by what number? We add these and divide by 9. So we get basically that mean. That would be the mean that would be called y1 ... Okay? And then the overall mean, which is the mean of all these numbers, that would be called y ... Alright? That is 2.90. So the first effect, alpha 1, is minus 0.16. Now you want to get the second, for the same factor, there are 3 effects, right? There are 3 levels. So the second one for A would be obtained how? What do we do for the second effect? Medium in row. We go this one, add this up, subtract the overall mean. Now, let's say for FIFO, we want to do medium. For FIFO, yeah, medium is actually easy. So all of these are easy because all the main effects are just in a row. So you can get all of these main effects. So these are the main effects. Alright? Now you will notice that the main effects by design add up to 0. So each row adds up to 0. So 0.16 minus 0.16, 0.02, and 0.14, they add up to 0, and so on and so forth. That is by design. Okay. Now let's see how do we do two-factor interactions. It is very similar to the previous one. Suppose we want to find out the interaction which has LRUV is small and FIFO medium. Then you take all the numbers that have that property. This one has LRUV is small and what is the FIFO value here? Hold on, this is previous page down, page up. LRU, FIFO, and those are actually 3 rows. I'm sorry, maybe I did something wrong here. First factor is A, it has 3 levels. LRUV, FIFO, and RAND. Second factor is blah, blah, blah. Okay, so let's just do it one more time, right? So LRU, the algorithm has 3 levels. LRUV, FIFO, and RAND. So to get the first level, we will add up these numbers. LRUV is the level, not the factor. LRUV is the level, right? Program is small, medium, large. So that is the second factor. But first factor for LRUV, we will add up all these numbers and divide by whatever number they are. Similarly for FIFO, we divide by that and then we divide by third. So this will be minus 0.16. This would be minus plus 0.02, and this would be 0.14. So those are the 3 for the algorithms. Let's see. 3 for the algorithms are minus 0.16, 0.02, and 0.14. So that is for the algorithm. Now for the program, for a small program, you will have to add up all the numbers of the programs are small. So they are basically this row plus this row plus this row. Alright? Those numbers added up and they were divided, that will give you the mean along that axis. Now if you want to find out the effect of groups, you have to take all the values where the group is 24p for that particular level, right? So these are all 24p, plus these are all 24p, plus these are all 24p. So you take those numbers. If you want to find out group is not a factor. Arrangement is a factor, group, frequency, and alpha. So I keep getting confused between the levels and the factor. This is basically, these are the three things, and then, so for this is deck arrangement, right? So for the deck arrangement group, you take all the values for which the deck arrangement is group, which is this value. And the last thing was memory pages. And the memory pages is not written here anywhere, but memory pages are, these are three memory pages, 24, 20, and 16. So you take all 24 P's, then divide by that, you get 24P value for memory. So basically that's the idea, is that you just take one level and one factor, fix it, get all the values, add them up. Right? Take the second level, third level, fourth level value, then you take the second factor, first level, second level, third level, and so on and so forth. So you get all these. Now to get the interaction, you have to take two things which are constants. Suppose you want to get the interaction A1, B1. We fix the level factor A at level 1 and fix the factor B at level 1, and whatever number of observations you get, you add them up, get their mean. Subtract the overall mean and you get, actually a little bit more complicated than that. Let me see. I haven't given you the formula for how to calculate the interactions, but this is in the book. So you can just look up that, in the book as to how to calculate these. But the value basically you do is that you subtract, so let's just do one at least. So you take, let's say we want to do algorithm is LRUB and the program is median. So we will take 53, program is median, algorithm is LRUB. I think all of these will have that property. The algorithm is LRUB and the program is median. And that's the only one set. So you add them up and then divide by the number here, whatever they are, and that will give you that mean. And then you have to subtract the overall mean. One thing I'm not sure is whether you have to subtract more than overall mean, but that is in the book. You can look that up. Anyway, so these guys did all the calculations for all the interactions, and then they found out all the effects and the sum of squares. Okay, so this slide shows the sum of squares. And from this slide, you see that the main effects explain 93%, which is good. First order interactions explain 4%, second order 0.98%, third order 0.14%. So really, if you didn't get anything below 5%, then you would not worry about any of the interactions. The main effects will do. Yeah. Yeah. Yeah, basically every time you have to take a mean, just remember you have to divide by the number of terms you added. Alright. Now they didn't have any errors in it because they didn't do replication. So there is no error term here. Alright. Now most of the interactions are small, except if you wanted to count one interaction which was significant, and that was this one, DM. DM is 1.96, you can see here percentage, everything else is smaller. right? So if you want it to be, if you even care for 1 or 2%, like this 1.96%, then you would include DM in the interaction. So they did that. Okay, so this is their model finally. 4 effects and interaction. One interaction. The way to write this, by the interaction values are given here, you get for each level of D and for each level of M, there is an interaction which is different. And so, they did have error computation. So what did happen to the applications? Oh, you know what? So what happens is, yeah, here is an interesting thing. So even though this is your model, right? So you're ignoring lots of other terms. Those can be put as an error, basically. In this particular model, the original model had no errors, right? But this model now has error because we are ignoring a lot of other things. So everything that is different from this model is counted as an error. And so now you can calculate the error for different experiments. And this is the number you will get if you just counted those 6 terms actually. In the previous slide, they had 6 terms: mean, 4 effects, and 1 interaction. 6 terms. So it's just error, then the rest is error, and now you can do whether they are normally distributed or not. So they are normally distributed except for one outlier. And they did verify that that was not an error. I mean, that was not an experiment. So there is a system behavior which happens at that point. Okay. One way to write this model, by the way, is to write down that the model is mean plus value of A. Depending upon A, you write down 0.16, 0.02, or 0.14. Then D, then P, then M, each of them at 3 levels, plus a matrix here, which you select based upon the D and M interaction, D level and M level, plus minus the standard error, which is the standard deviation of error. So this is another term that you will see quite a bit. I don't know whether we introduced this so far, but standard deviation of error is also called standard error. Okay, and plus minus 0.12. Okay. And when you write a model, it is good to write down the levels right there so people know what 02 is, what 54 rand is for this, and so on and so forth, so people can make a relationship. And similarly, if there is a choice, I would put here M values and the D values here, which are actually here. And we could put group frequency and alpha and 24P, 20P, 16P, whatever. Everybody understands how to interpret this model? Right? It's complicated because there are so many levels, so many things, but you have now all of these things analyzed. All right. So this is the method that you will do if you're doing writing a paper or something like that. But there is another simpler method, set of methods that generally work better and turns out in the usual world, because it's difficult to explain all these effects and interactions and this and that. So we'll talk about those here. For example, sometimes you really don't care what is the effect of each factor. You really want to find out what is the best combination. Just you need one answer. That among all these 25 or 30 combinations with, let's see how many combinations, 81 combinations, right? 81 combinations we did. This is the one that is the best, or something like that, whichever number, right? And because those are all the parameters that are going to fix in your algorithm. If that is the case, then you really don't need to do kind of analysis which we did. You just go and find the max. So anyway, Second one is observation method, and I'm going to show this as an example. In this case, we had 5 factors, and they did 2 raised to 5 minus 1 design. So they had 2 raised to 4, 16 observations, 16 experiments. Here are the 16 numbers. 5, here are the 5 factors, A, B, C, D, E. All right, and they have 3 different metrics. Okay, this is throughput for the workload. Okay, this was the throughput for the word processing, throughput for the interactive data processing, and throughput for background data processing. So they have 3 different classes of job, and they measure for each of them. And so for the word processing, you can see that the highest is 28. Highest is 28 when A is minus 1, B is 1, C is 1, D is minus 1, and E is 1. That's all here. All right. However, you can do one better. Look at the second best. Second best is 27, which is very close. And in that case, A, B, C, D is as follows. Now what you do is you combine the two. You see A is always minus 1 in both cases. B is plus 1 in both cases. C is changing the sign. D is changing the sign. E is same. So you can make another statement. You can say, well, if you really want to keep high throughput, it's important that you do A, B at these levels and E at this level, and C and D are, like they're not that critical actually. Because if you C plus, C minus, you still get 27, which is very close to the maximum. Right? Similarly, D is not critical. If you had done the complete 2 raised to 5 minus 1 analysis, which you can do in this case, you would have found out the importance of C and D would be small. Okay, but you can observe that right here, because then you could do even one more better. What could you do one more better? Is that you could take the third best. What is the third best here? 25. Right? And then you could set the sign and see if something holds still. So you see, my A is still minus 1 in all 4 cases. Right? So that is the most important thing to do, that A has to be minus 1. Now, can you do better than third best? Anybody? What can you do more? Take it up how many? What do you think of doing better than top 3? Take it top 4. Take it top 5. In fact, what you should do is you should sort it out and take as many as you can. Right? So, anyway, the conclusion based upon that analysis was that there should not be any preemption. A should always be minus 1. B should always be plus 1. The slice should be large. The fairness should be on E. And the Q assignment and decoupling do not matter. So that was the initial calculation, right? But ranking method is one where you sort it out. This is the second method. That we sort it out the R from top to bottom. Alright? And then we look at the signs. So you can see for all the top, A is minus 1, for all the bottom, A is plus 1. So the conclusion is that really if you want to get high throughput, A should be minus 1. What about B? B is, plus 1 here on the top. And so that one also gives something that, it might help to have plus 1. For C, we have minus 1 plus 1 and minus 1 plus 1 plus 1 minus 1. And actually minus 1 is negative. So you can make a statement that don't keep it minus 1. It doesn't really matter, but if you have a choice, keep it plus 1. Because minus 1 gives you lowest values. For D, you can't really find any consistent thing. For E, top and bottom both have plus 1. So it's really no recommendation there. The only way you can make a recommendation is that if you made a statement about the other factors, if you somehow you have to keep A equal to plus 1, then you keep E equal to plus, so you cannot consider that. So, but anyway, for the top things, you can still make the same kind of observation to say that if A equal to minus 1, E equal to plus 1, E equal to 1, and most important thing is A. Second important thing is B. Yeah, go ahead. This one? Yeah, so the thing is these two are 10. The difference between these two rows are only B different, C is different, those are two differences, right? And so somehow, I mean, really, I mean, this kind of experiment is very difficult to make. I mean, see, the thing is, what I was saying was, in some cases, you are interested in maximizing the implement the sum of the rows. In some cases, you are interested in minimizing, like response time. You look at the bottom rows and see where is the consistency from the bottom, right? And here is consistency, there is no consistency here, there is consistency a little bit, no consistency here. So the thing is, if you are, so the question is, would I keep C equal to minus 1 or plus 1, looking from the bottom? I mean, that's a good observation, at least in this case, that really C doesn't really matter because, it's somehow interacting with B, and if B is plus 1, it is minus 1, if B is minus 1, it is plus 1. So this is the interaction that is counting here. Okay, so here's the thing. In the real world situation, I wouldn't do any of this for 16 observations. I mean, I can just, my Excel worksheet will do the correct analysis, right? But if you have 256 observations or, or 2056 observations, then, and here is another thing, and your goal is not really to quantify the effects, your goal is to find the best. Then you don't have to do the analysis to find the best. I mean, you could very easily just take the best. But the reason you don't want to take just the best is because the next best cannot be that bad. And if it is not that bad, then why work hard to fix those factors? Right? So you want to study how smooth that surface is, like we said. So this y is the surface, right? And if the surface is very flat, then it doesn't matter where you put the parameters. If the surface is very peaky, then you want to put it at some place. So that's what this is showing. So the idea is if you just want to get the best of the worst, then this doesn't work. All right. The last one is the range method. In the range method, you just find out the minimum and the maximum. So in the analysis that we just did for the case study, and we did the log and everything else, before taking the log, these are the numbers. What we have here is the range. So when the replacement algorithm is at level 1, the range is 2056. Range means minimum minus maximum minus minimum. So let's go back and see. When the algorithm is the first range, first level, this one, the minimum is 32, the maximum is 12,888, right? So the range is 12,800 something, right? Okay, let's see what do we have here. Replacement algorithm, maximum minus minimum is 2056. 2056 for level 1. For level 2, 2986. For level 3, 3781. Let's go back and check. It doesn't come out with the number that I am thinking about. So for algorithm A is the algorithm, right? Can I have the slides so I can see two things at the same time? Yeah. The ranges are more like 17,000, 12,000. All right. All right. I will have to figure out how these numbers came about. I think these numbers are probably missing something. But assuming that these numbers are correct somehow, and I will let you know later on, then the next step is to find a range. So from 1 to 3, the range changes from 2056 to 3781. And so that the minimum and maximum is the 1725. Here it is 2725, it is 5,000, here is 6,000. Okay? So anything that has a lot more variation is clearly has more effect. All right. So we would say that memory has lot of effect. Program has next effect. Deck arrangement is the next effect, and the replacement algorithm have smallest effect by this data. Yeah. Averages over 2056. Okay. So that was that. Oh, let me go. Let's just verify that. I will check that out because it won't be easy for me to verify that either. So what he's saying is that if you take the average of this, then you get 2,000. And I will have to verify that. I in fact might have an Excel worksheet to calculate that 2,000 somewhere. So anyway, so basically, that might be the case. But anyway, so once you get that, then anything that has the maximum range gives you. So it's quite possible actually. What it says that the range is done here. This is the mean. So this is the mean, and this is the range of the mean. Range of the mean. That brings us to the end of this chapter and the end of experimental design. And this key thing is that you can have any number of factors, any number of levels, and the more factors, more levels you have, more interactions you have. Okay? Generally, the high level interaction, as we saw in this case, is smaller and smaller and smaller. So while there are so much complexity, at the end you might find out that really the main effects and the first order interactions might be okay. And then if you really want to find out only what is the best, what is the worst, or something like that, then you do the observation method, the ranking method, or the range method. Okay, there is homework. And this is the same thing that we have in the study, except that you have to analyze this set of things, and you can do by observation and ranking method. So you can find the top and rank that out as to what you need to do.